Hi, this is the fifth lesson in waves. See the description of this video. There, all the links related to the first four videos are given. In my first video or first lesson related to waves, I discussed about phase relationship and the basic properties of the waves. In second lesson, I discussed about intensity of waves. Third lesson, I discussed diffraction. Fourth lesson, I discussed refraction. This is the fifth lesson. And you can navigate to any of my video by using the playlist of this channel. I grouped all my 115 videos into different groups, such as uh, lesson in unit 1, past paper discussion related to unit 1, lesson in unit 2, past paper discussions in unit 2, and so on like that. So by using the playlist of this channel, you can navigate to any required video. By using the description of this video, you can also go to the important videos or necessary videos related to waves. Right, okay. In this video, that is the fifth lesson in waves, I am going to discuss wave interference or interference of waves. Okay, what is interference of waves? Is the phenomenon that describes about when two or more waves overlap, what could be the outcome? So in your syllabus, we consider superposition of just two waves, but actually there could be more than two waves superposed at a point. So we need a principle to analyze or to analyze the outcome of the superposition. That principle is called principle of superposition. So principle of superposition says that when two or more waves overlap or superpose at a point, the resultant displacement is equal to the vector sum of the displacement of each and every individual waves overlapping at that point. Again, I'm saying the principle of superposition says that the resultant displacement at a point is equal to vector sum of the displacements of each and every individual waves overlapping or superposed at that point. That is the principle of superposition, but it says about vector sum. So we can show the principle of superposition by using a wave pattern. What could be the outcome, how to get the outcome of superposition. So I'll draw it and explain the outcome of superposition based on principle of superposition. Okay, so I showed by using wave diagrams, wave patterns, what could be the outcome during two different situations. The first situation, if the waves overlap in phase. Okay, the waves overlap in phase means the crest and crest should overlap at a point, or trough and trough should overlap at a point. So if that happens, they will reinforce each other. That means the outcome will be much stronger. The amplitudes will be added. The principle of superposition says that vector sum of the displacement, so the amplitudes are in the same direction, so the amplitudes will be added, so the outcome will be with a larger amplitude. We call that as constructive superposition. We say the waves are overlapping in phase. Waves are overlapping in phase at a point means crest and crest. Crest of the first wave and the crest of the second wave should overlap at that point. Trough and the first wave and the trough of the second wave also should overlap at that point. So if crest and crest overlaps, trough and trough overlaps for the two waves, then that type of superposition is called constructive superposition. Okay, so that will reinforce each other, so the outcome will be stronger. The wave pattern will have the same frequency, same wavelength in this one, in this situation, but the outcome, the amplitude should be added up. Okay, so when the waves overlap like this, in which crest of the wave and trough of the second wave, or trough of the first wave and the crest of the second wave, if they overlap, we say they are overlapping antiphase at that point. Antiphase means, according to vector sum, one has displacement in one direction, the other one has the displacement opposite direction. So we need to find the difference of it. Yes, we need to find the difference of it, because principle of superposition is vector sum of the displacement at that point. So here the displacement for the first wave drawn in blue color, the displacement is upwards. For the second wave, downwards is the displacement. But here for the second wave, displacement is upwards, that's amplitude. Here this is downwards. So we need to find the difference of the amplitudes. So the resultant wave pattern will be having a amplitude, which is the difference of the amplitude of the two waves. We call that as destructive superposition. So destructive superposition is happening at a point means, in your syllabus we consider only two waves. Practically there could be more than two waves overlap, but for simplicity in your syllabus we consider only superposition of two waves, right? Okay, so I'll talk about only superposition of two waves. So when two waves overlap at a point, if they overlap such that crest of one wave and trough of the other wave, or trough of first wave and crest of second wave, we say the waves are overlapping antiphase and destructive superposition is occurring. We call that type of superposition as destructive superposition. So you must know the conditions to have constructive superposition and destructive superposition. Constructive superposition means the two waves should overlap in phase. What do you mean by in phase? Crest and crest should overlap, trough and trough should overlap. Destructive superposition means they should overlap antiphase. That means crest of one wave and trough of the second wave. Other way, if I say trough of one wave and crest of the other wave, if they overlap like that, we say they are overlapping antiphase. Destructive superposition will occur. So here I took they have different amplitudes. In case if the two waves have the same amplitude, that is A1 is equal to A2, if the amplitude A1 is equal to A2, so here we took A2 minus A1, A2 minus A1. So what will be the resultant? The resultant wave pattern is nothing. There won't be any wave. So the wave pattern is straight line. There is no wave. It's completely gone. We can, anyway, I can use the word, they cancel each other. We can use the word, they cancel each other. There will be complete cancellation. Okay, there will be complete cancellation if they have same amplitude, and when they overlap antiphase, there will be complete cancellation. Okay, so in my first lesson I explained about phase and phase difference of a wave. In my first lesson, I give the link in the description of this video. In my first lesson I explained about phase and phase difference of a wave, right? When we consider 2 points of a same wave, what could be the phase difference between 2 points? And I told what is phase. It's actually in terms of radians or degree we give. But here we need the little bit of mathematical approach also. Here we need that. So if two waves are overlapping in phase at a point, careful, the waves are overlapping in phase at a point. They overlap at a point, physically at a point. So if the two waves are overlapping in phase at a point, then the phase difference between the two waves, when the waves are overlapping in phase at a point, the phase difference between the two waves, here two waves overlapping, phase difference between the two waves could be either 0 or 2 pi radians or 4 pi radians or 6 pi and so on. That will be even number of pi, 2 and pi radians. So at a point, if the two waves are overlapping in phase, then the phase difference between the two waves at that point could be either 0 or 2 pi or 4 pi, 6 pi and so on, even number of pi. Same way, if the two waves are overlapping at a point antiphase, not out of phase, antiphase among them, then the phase difference between two waves could be either pi or 3 pi or 5 pi, or you can say 2n plus 1 pi or multiple of pi. So if the two waves are overlapping antiphase, then the phase difference between the two waves at that particular point must be either pi or 3 pi or 5 pi. I didn't put the or, anyway you know that, 5 pi or 7 pi. That means odd multiple of pi, that is general format of odd multiple 2n plus 1 pi. Okay, that's the required condition. Remember this, that won't be given in the question paper. You must remember what's the phase difference between the two waves at a point if they overlap in phase. These are the phase difference. If they overlap antiphase, these are the phase difference. There could be out of phase. Yeah, the two waves might overlap out of phase at a point. Out of phase means neither. That means it's not this format. It's not this format. Maybe the phase difference may be pi by 2 or 3 pi by 2 or 4 pi by 6, something like that. So then they are also overlapping happening, but the phase difference is something else and we don't consider that because this is something related to applications. So all the applications related to superposition of waves depends on either constructive superposition or destructive superposition. There are a lot of applications related to superposition of waves. Anyway, you don't need much about it. One thing is by using the superposition of waves, we can find the wavelength of a particular wave. Say for example, if we are by using the superposition of light, of monochromatic light, one particular color light, we can find the wavelength of that light. Similarly, by using superposition of waves, there are many other applications like thin film coatings. That means they avoid unwanted reflections from the lenses, so they put a thin coating on the outer surface of the lens such that the reflected waves overlap destructively and cancel each other, so that we can minimize the unwanted reflection from the lens. And hologram, there we need the superposition of waves. Interferometers are used to measure very tiny lengths, something in the order of 10 to the power minus 9 meter up to nanometer. We can measure the length, something like it's very useful in technology industry, something like in the form of microchips, designing those things. And also communication technology, filtering unwanted noise, there we use the superposition of waves. Color filters, like there are a lot of applications are there based on superposition of waves. In all those applications, we consider either constructive superposition or destructive superposition. We don't want any superposition out of phase. Due to out of phase, something like neither of the phase difference. So that's the reason students normally ask, why don't we consider other type of phase differences when we talk about superposition? Because they don't have any significant applications. Okay, so that's the reason we don't consider any other phase difference other than these phase difference or this phase, because they don't have any useful applications. Okay, I hope you understood the reason why we consider either constructive or destructive. Neither we don't consider. Okay, so superposition pattern. What do you mean by superposition pattern? It's actually the superposition pattern could be shown by a graph, or it could be shown by a diagram. Yeah, that's the way we do show the superposition pattern, either in the form of graph or diagram. So what do you mean by superposition pattern? Means when two or more waves overlap, how the results comes in different points in the space. Say for example, when we consider, imagine there are two loudspeakers. There are two loudspeakers, L1 and L2. Okay, so imagine they are emitting, they are connected to a signal generator, so they are emitting same frequency of sound, right? Same frequency of sound they are emitting. Okay, so when you consider a point in space, somewhere here, the point P1, the sound is emitted from the loudspeaker L1 is reaching the point P1. The sound emitted from the loudspeaker L2 also reaching the point P1. Both loudspeakers are connected to the same signal generator, and the signal generator is emitting same frequency of AC signal. So this is signal generator. So the both loudspeakers will emit same frequency of sound. Okay, so these two sound waves emitted from L1 and L2 are reaching the point P1. So they are going to overlap at point P1. So I told in terms of applications, useful applications of superposition, we consider either constructive superposition or destructive superposition. I told there are many applications. Just now I told there are many applications related to superposition of waves. We consider only the constructive or destructive superposition. Neither we don't consider out of phase superpositions. We don't consider. Okay, so at point P1, if the waves are overlapping in phase, and if you are doing this experiment in a very silent, larger room or larger hall, we avoid all the reflections from the wall, and it's a very silent hall, so there won't be any other sound other than the sound emitted by the two loudspeakers. So if the two waves are overlapping in phase at point P1, you will get a louder sound at point P1. If the two waves are overlapping another point at P2, they are overlapping antiphase. Destructive superposition occurs means at point P2 you will hear much lower intensity of sound or no sound at P2. Same way at P3, if you are getting louder sound, that means the two waves are overlapping at P3 constructively. So in phase superposition is happening. So you will hear louder sound. So like that in space at different points you will get either constructive or destructive superposition, louder sound or no sound. In between we don't consider, I told that. So either louder sound or no sound points we are identifying in the space. I can mark the specific points in space, say this is louder sound, here no sound, and for no sound here louder sound, here no sound, like that. I can mark in space in that hall different locations by louder sound, no sound regions. This is called superposition pattern. This is called superposition pattern. So here I can show a graph by using in terms of distance. I can start distance from here, from this distance, how the loudness is varying. I can show by a graph, or I can show it like a diagram like this way. Anyway, whatever I show, this is called superposition pattern, right? The superposition patterns we need in applications. Say for example, by using this method, we can find the wavelength of the sound. By using this method, yes, we can find the wavelength of the sound emitted by the loudspeakers. I told both are emitting identical sound, and by using the wavelength of the sound, we can find the speed of the sound in air. I'll do a question based on this later in this lesson. I'll do it. But we need a superposition pattern like this for our useful applications. So okay, so I told that this at point, this is louder sound, no sound, like that. They are forming. This superposition pattern must be stable. That means it remains same throughout the experiment. So for example, here you got a loud sound. Within 1 second, if it becomes no sound, then here you say got no sound. If this becomes louder sound in 1 or 2 seconds, like that, if the superposition pattern formed in space are changing with time, randomly changing with time, then it is not useful in terms of applications. We can't do any proper applications by using such that unstable superposition pattern. So for any useful applications, I told that there are many applications like thin film coatings at anti-reflecting surface on lenses. Not in your syllabus, we don't use that, but these are the applications related to superposition of waves, hologram. Then interferometers, those are used to measure this tiny lens, or when you are planting tiny microchips in designing, we need very small measurements in terms of micrometer orders. Yeah, the superposition patterns are used, superposition of light. Then communication technologies where we are filtering unwanted noises. So anyway, in all these applications, we need a stable superposition pattern, right? So if we have stable superposition pattern, that means we can do useful application by them by using these stable application, stable superposition patterns. Okay, so what is the condition to have this stable superposition pattern? We say the waves emitted by the two wave sources. Here I took just an example, two loudspeakers, but any two wave sources where we are using for our purpose, right? So that the waves emitted by the wave sources must be coherent among them. They must be coherent. So what do you mean by coherent waves? So to have a stable superposition pattern, we must have coherent waves. So what you mean by coherent waves means the two waves must have the same frequency. They can't have different frequency. First condition, they must have the same frequency. The second condition, the phase relationship between the two waves should remain constant at a point. So what do you mean by that? Why should it have same frequency? Means actually difficult to draw and explain. It's like this. For example, I try to draw, but it's very difficult to draw. But there are a lot of animations in the internet. You can see them. There they are clearly explaining by using animations. Okay, I somewhat drew, but it's not easy to draw. Imagine a point where always destructive superposition occurring. Say for example, the crest of this wave reaches this point, the trough of the wave will reach that point, because both waves will move at the same speed, both have the same wavelength. So if this crest moves this point, trough will reach the same point. When the trough of the first wave, which is emitted from L1, when the trough of this one reaches this one, crest of this one will reach. So again, trough and crest overlapping, antiphase superposition. When the crest of this one moves here, trough of this one moves here. When the trough of this one moves, crest of this one. You can line up like this. So the waves are, if the two waves are coherent, means the crest and trough of the two waves are lined up like this. They line up like this and they will reach always the same way. That is, when the crest of this one reaches this point, trough of this one will reach that point. When the trough of this one reaches this point, crest of this one will reach. When the crest of this one reaches, trough of this one reach. When the trough of this one reach, when the crest of this reach. So like that, always the crest and trough will always reach at that point. That will form a destructive superposition at this point. So to have such stable superposition pattern, so then it will be always stable. That happens only when both waves have the same frequency. That means same wavelength, both identical waves, so they have the same speed. If they have same speed, they should have same speed because they are similar type of waves, so they should have the same speed. If they have same frequency, then they will have the same wavelength. If they have same wavelength, this will happen. When crest comes here, trough will come here. When trough comes here, crest will come here, and so on. I can say the crest and trough of the two waves are lined up together because they are coherent waves. That is one condition. Second condition, they should have the same phase relationship. Due to some reason, if the loudspeaker either L1 or L2 changes its way, the pattern of emission, then at the start the wave pattern will change the way of emission. So if the phase relationship between L1 and L2 randomly changes, that will affect the whole region. So at this point, then the crest and trough will not reach always, even if they have the same frequency. Actually accept it because difficult to explain other than by using proper graphics. Yeah. So, but anyway, if there's a sudden change in the phase relationship at the point of emission, then what happens? That will change the whole wave transmission. So at the point, this will not happen. So when crest comes, here there could be crest also reach the same point. So a point where destructive superposition happening might becomes as a constructive superposition, then it will become unstable superposition pattern. Okay, so to have the stable superposition pattern, they should have the same wavelength, means same frequency. They should have the both waves. The second, the phase relationship between the two waves should remain constant. The phase relationship should remain unchanged. So a source that emits, two sources, those emit coherent waves is called coherent wave sources. So coherent wave sources means the wave sources, those emit coherent waves is called coherent wave sources. So the coherent waves means the two waves. So past papers several times they ask what is coherent waves. Coherent waves means they should have the same frequency and constant phase relationship. That is called coherent waves. Why should we have coherent waves? To have a stable superposition pattern. So if the waves are incoherent, that means they are not coherent. Will there be superposition? Yes, there will be superposition, but it will be unstable superposition. Unstable superposition means we won't be able to do any measurements. There is no useful application, but there will be superposition even when incoherent waves. That means the waves, those are not coherent. When they overlap, there will be superposition, but the superposition pattern will scroll. We say scroll or change with time. We can't do any measurements, so it's not applicable in a useful way. Okay, so we know the meaning of coherent waves and coherent wave sources. Why do we need to have a stable superposition pattern? We need coherent waves. The wave sources, those emit coherent waves, are called coherent wave sources. Okay, practically how can we get coherent wave sources? Okay, how can we get coherent waves? Okay, the first one, how to get coherent sound waves. So first condition, coherent waves means they should have same frequency. The second condition, the phase relationship between the two sound waves must be constant, right? The phase relationship should remain constant. Okay, so students normally they ask, can't we use two different loudspeakers connected to two different signal generators? You know, when you connect a signal generator to a loudspeaker, signal generator emits AC signal, or it gives out AC alternating current. So for example, if the signal generator gives out 2000 hertz of sound AC signal, and when you connect that sound to a loudspeaker, that AC signal to a loudspeaker, then the diaphragm of the loudspeaker will vibrate at the same frequency as the AC signal from the signal generator. Say for example, it will emit, if the signal generator emits 2000 hertz AC signal, the diaphragm will vibrate at 2000 hertz, so the sound will be emitted with a frequency of 2000 hertz. So students normally ask, can't we have two different loudspeakers connected to two different signal generators? So this is a loudspeaker L1, this is a signal generator connected to this loudspeaker, then second loudspeaker L2 connected to the identical signal generator. So this is signal generator first one, signal generator S2. Can't we keep both signal generator output at the same frequency? Yes, you can have. Say for example, the output of S1 could be 2000 hertz. From S2 also 2000 hertz AC output. Then both will emit same frequency of sound, 2000 hertz. That means they will have the same wavelength, no problem. But the problem is the phase relationship between the two outputs won't remain constant. The reason is two signal generator, they are independent to electronic devices. So even if they are emitting same frequency of AC signal, the problem is the phase relationship between the output might change. Suddenly the one wave signal might lag from the second one, or it might lead from the second one. So the phase relationship between the two output of the two loudspeakers, the output of the two signal generators won't remain same or won't remain constant. The phase relationship won't remain constant. Even if they are emitting same frequency of AC signal, same frequency of sound, the phase relationship won't remain the same. The phase relationship might change because they are made of electronic components. So due to that reason, it could change. So to avoid this problem, what should we do? We should connect both loudspeakers to the same signal generator. So we should connect both loudspeakers to the same signal generator. So this loudspeaker get AC signal from the signal generator, L2 also getting from the same signal generator. So both are having the same frequency, 2000 hertz, 2000 hertz. Now, as I told earlier, the signal generators are made of electronic components inside. There could be change in the phase if we have two different signal generators, because one might lag the other one might lead the other. So there could be small changes in the phase relationship. But when you connect the two loudspeakers to the same signal generator, whatever the changes happened here will affect the both. So if there is change, or maybe it's a very small time, it has a delay, whatever happens to the first loudspeaker, that will happen to the second loudspeaker also. So the phase relationship will remain constant. Okay, when you connect the two loudspeakers to the same signal generator, whatever changes happen to L1 will happen to L2 also. So the phase relationship will remain constant. Then they are emitting the same frequency. So the sound waves emitted by the two loudspeakers L1 and L2, those are connected to the same signal generator. The sound waves emitted from L1 and L2 will be coherent waves. So that's the way we create coherent sound waves from the two loudspeakers, but we must use the same signal generator. Okay, so monochromatic means one wavelength or one color light. How to create one particular color? We can use the same frequency of light, that's not an issue. We can use color filters, it's not an issue. But how to get the coherent light? So it emits only one frequency, one wavelength. We can be the same frequency of color, but how to get the coherent waves? We can't use two different bulbs. If you use two different bulbs or light sources with the same color, can they be coherent light sources? No, they won't coherent waves, because you know any light source or any bulb that emits light as continuous bursts. So different points on the bulb emits light at different instances, like a continuous burst. So the phase relationship will randomly change when you consider two different bulbs. So if you have two different bulbs and if you keep a screen or whatever the sensors here, you won't get any superposition pattern. So the light will just fall on the screen. You will see just everywhere the same intensity of light, because the waves emitted by the two bulbs or two lamps or two light sources have the same frequency if you are using same color monochromatic, but they emit light as continuous random bursts. So the phase relationship will randomly continuously change. So since they are incoherent waves, the superposition will happen on the screen if you keep a screen, but the superposition pattern will very fast change or scroll. So it will actually, the superposition pattern will be washed off. You won't see any superposition pattern, right? So then students, they ask, can't we use, okay, the two different bulbs we can't use because they emit light randomly. So we can't use like this, okay, in front of a double slit, you know, double slit, young slit, in front of double slit, if I keep a bulb like this, something like this way, if I keep a bulb like that, and if I keep a screen here, will I be able to get a superposition pattern here? Because the two lights, two slits S1 and S2 are going to receive the light from the same bulb. So whatever happens in this bulb will affect both the light passing through the slits. So the light coming out of these two slits, won't they be coherent? Again, they won't be coherent, because the slit S1 might receive or might get light from a certain portion of the bulb, and S2 might get light from some other portion of the bulb. I told each and every point of the bulb emit light randomly as continuous bursts. But we don't feel it. When you see a bulb, it looks like the whole bulb is emitting light at the same time. But actually, different points of the bulbs, they emit light at different times. So the phase relationship between any 2 points, the light from the any 2 points will randomly change. So if you have a double slit and in front of it, if you keep a monochromatic bulb, there are also the light rays coming out of the two slits won't be coherent, because slit S1 might receive light from certain portion of the bulb, S2 might be from some other portion. So they are independently emitting light, so continuous burst, so they won't, the light from the S1 S2 won't be coherent. So what shall we do now? We should use a single slit like this. We should use a single slit, then double slit, and keep the bulb here. Okay, now what happens? The two slits S1 and S2, this is S, the slit, single slit S. Okay, the S1 and S2 won't receive the light directly from the coherent bulb source. They can't see the bulb directly because slit S is blocking. But S1 and S2 receive the light that is diffracted through S. So for S1 and S2, S is the light source. So the S might receive light from different portion of the bulb, whatever it is. S might receive light from different portion of the bulb. That doesn't matter. That light will diffract when it passes through the S. So the same light is going to pass through S1 and S2, which is diffracted by S. So whatever changes happening at S, whatever the phase change happens at S, will happen for the light coming out through S1 and S2. The same phase change will happen for both S1 and S2. When same phase change happens for both S1 and S2, the phase difference will remain constant. Understand? So the S1 and S2 will receive the light that is diffracted by S. So S is receiving light from different parts of the bulb. That's not a problem. Whatever changes happen here will happen for both lights coming out through S1 and S2, because S1 and S2 are receiving light from S. Same thing. So S1 and S2 are receiving light from the same slit S. So whatever phase change happens at S1 will happen at S2 also. So the phase difference will remain unchanged. The phase difference remain the same. So phase difference remain the same. It's a monochromatic bulb source. So one wavelength. So it's same frequency. So the light coming out through S1, S2 will be coherent. So here, what is which is the coherent light source in this practical? The slits S1 and S2. Slits S1 and S2 are the coherent sources, because the light coming out through S1 and S2 acts as coherent waves. Okay, so when you consider two different laser torch lights or two different laser beams from two different torch lights, so this is the first laser torch, this is the second laser torch. Okay, so there, when you consider the wave or the laser light emitted by two different laser torch, there will be random phase change between the two waves. So you can't use two different laser torch lights as coherent wave sources or coherent light sources, because the phase relationship between two laser torches, the laser lights will randomly change. You don't need how laser torch emits light. Anyway, the principle is different. But anyway, the two laser lights won't have constant phase relationship. But when you consider one laser torch, yes, in which the phase might change, but every point on the laser torch, if I see the front part, if the laser light is coming through this laser torch in large diagram, so the laser is emitted from different points, the light is coming out of the board. So when we consider laser beams or laser light coming out of this laser torch, the phase will change, but when you consider any 2 points, the phase change will be always the same. When you consider two different laser torches, yes, the phase difference between two laser lights from two laser torches will randomly change. But when you consider one laser torch in which the phase relationship will happen the same way everywhere, so we can say whatever the change occurs here will occur here, also will occur everywhere. So the laser light from a particular laser torch, among them they are coherent. So by using one laser torch, we can't how to design a superposition pattern. We need two coherent waves, but we have only one laser torch. So the light from one laser torch should allow to pass through double slits. So here we don't need single slit. Here we don't need single slit. The light from the laser torch, let it pass through two slits S1 and S2. Then if you keep a screen here, you can see the superposition pattern. Here we don't need single slit because the phase relationship between any ray coming out of the laser torch, the phase relationship among them is constant. So it's a coherent wave source. So therefore, we can let the laser torch, the laser light to pass through two slits. Then the light coming out through these S1 and S2 overlap and form the superposition pattern. So when we are using laser light or laser torch, we don't need single slit. For bulb, as I explained earlier, normal bulb or normal lamp, we must use a single slit also. Okay, so if you want to generate coherent waves in ripple tank, in water waves, the same electric motor or the vibrator must be connected to the two dippers. We can't use two different electric motor with two different single dippers. The double dippers which hit the water surface must be connected to the same electrical vibrator or same motor. So both will vibrate exactly the same way. So the wave generated by the two dippers on the surface of water will be coherent waves. Okay, so the next topic is path difference. Path difference is the difference between the distance traveled by the waves towards a point. So we already discussed coherent waves. So in your syllabus we consider two waves superposition. So already we learned that to have constructive superposition, the required phase difference should be either 0 or 2 pi or 4 pi and so on, even number of pi. To have destructive superposition, the phase difference should be pi, 3 pi, 5 pi and so on, or multiple of pi. But phase difference is not a measurable quantity. It's actually a property of the wave equation. Go through my first lesson there. I showed what is phase and phase difference. It's something related to the wave equation. But path difference is a measurable quantity. So in space, when we have two coherent sources, at different points in space, different type of superpositions will occur. At certain points, there will be constructive superposition. At certain points in space, space means just in a location, different locations. If you have two loudspeakers, I told earlier, at different points, you might hear louder sound. Certain points you won't hear any sound. So louder sound is due to constructive superposition, no sound is due to destructive superposition. Like that in space, at different locations or different points, different type of superpositions will occur. The distinct property that or distinct factor that decides the type of superposition, whether it's going to be a constructive superposition or destructive superposition, is the path difference. Remember that. It's a measurable quantity. All your calculations related to interference, where you need to calculate what type of superposition will occur, there we use path difference, not the phase difference, because phase difference is not a measurable quantity. We can calculate it, but it's not a measurable quantity. So path difference is the distinct factor that decides the type of superposition that happens in space at different locations or at a point in space. So what is path difference? Is the difference between the distance traveled by the waves. Consider here S1, S2 are sorry, S1, S2 are two coherent wave sources or slits. I already explained that. We can create coherent waves from two slits. So S1, S2 are the coherent sources. They emit coherent waves, means they should have the same wavelength, same frequency, constant phase relationship. So they are overlapping at point P. The distance traveled by the wave from S1 to SP is this distance. We can measure this distance. I can give the distance in terms of wavelength. What's the distance from S1 to P? S1P, the distance in terms of wavelength is from here to here 1 wavelength, 2, 3, 4, 4.5 wavelength, that is 4.5 wavelength. Same way, distance from S2 to P, the superposition is happening at P1. We are considering the superposition at point P1 in space. So what's the way distance of S2 to P? That is 1, 2, 3, 4, 5. Yes, 5 lambda, is it? I couldn't draw nicely. There are good animations in the internet, but I try to draw it. So S2P, the distance is from here 1, 2, 3, 4, 5. That is 5 lambda. So I can give the distance of S1P and S2P in terms of wavelength. What is path difference? Difference between the distance traveled by the wave. So the path difference here is S2P because S2P is larger. Path difference equal S2P minus S1P, that is 5 lambda minus 4.5 lambda, that is 0.5 lambda. I can say half lambda or lambda by 2, half lambda, or 0.5 lambda, I can say lambda by 2. So the path difference is lambda by 2. When I consider this diagram, here S1, S2 are the two coherent wave sources. So here they are overlapping at P2. Here you can see that what type of superposition is happening. Trough of the wave from S1, trough of the wave from S1 is overlapping with crest of the wave from S2. So trough and crest are overlapping. When this wave reaches the point P, because the wave is, both waves will have the same speed because they are similar waves moving in the same medium, they'll have the same speed. So when the crest moves here, trough will move here. When the trough moves here, crest will move here. When the crest moves here, trough will move here. So that means they are going to form always at point P destructive superposition, right? When you consider this diagram here, S1, S2 are the two coherent wave sources. So the distance of S1P, the distance of S1P is equal to, I can give it in terms of wavelength. S1P is equal to 1, 2, 3, 4, 5, 5.5, 5.5 lambda. Same way, distance of P2 from S2, that is 1, 2, 3, 4, 5, 6, 6.5, 6.5. I couldn't draw a nice diagram, I'm not a good artist, but anyway, I just try to draw. So 6.5 lambda. So here the path difference equal to S2P minus S1P, that is 6.5 lambda minus 5.5 lambda, that is lambda. And we know at P2, the point P2, what type of superposition will happen. Here the trough and trough are overlapping. At that moment, trough and trough overlapping. Then crest and crest will over. Then this crest reaches this point, the crest will reach that point. When this trough reaches, this trough will reach. When this crest reaches this crest, both are moving at the same speed, both waves. When this trough reaches, this trough will reach. So, you know, crest and trough are line up together. They are coherent wave sources. So, there will be constructive superposition. So, you can see here destructive superposition. It's a stable superposition pattern because the waves are coherent wave sources and waves are coherent. So, at P1, always there will be destructive superposition going to happen. So there will be destructive superposition. This will form destructive superposition. Here it's going to form constructive, crest and crest, trough and trough, crest and crest. So there will be constructive superposition. So to have destructive superposition, we know the path difference should be lambda by 2. To have constructive superposition, the path difference should be lambda, but that is not the required path difference. We can imagine there could be a path difference lambda by 2 means crest and trough will overlap. Again, think like that. If you are interested, you can draw and see if the path difference is 3 lambda by 2, that is 1.5 lambda, 3 lambda by 2. Again there will be a point in this space. You can imagine a point in space in which the path difference, the difference between the distance traveled by the wave, if it becomes 3 lambda by 2, that is 3 lambda by 2 means 1.5 lambda, 3 lambda by 2. If there is a point something else here, for that point the path difference is 3 lambda by 2. At that point destructive superposition will occur. Again, there could be a point in this space somewhere here or further up. It could be 5 lambda by 2, that is 2.5 lambda. If the path difference is 2.5 lambda, that is 5 lambda by 2. Again, there will be destructive superposition. 7 lambda by 2, that is 3.5 lambda. Again, there will be destructive superposition and so on. Here, the path difference is lambda. If you consider the central point, if you consider exactly the midpoint where both will travel the same distance, is it exactly midpoint, both will travel the same distance, so path difference will be equal to 0. There also constructive superposition will occur. When the path difference lambda, there will be constructive superposition. Crest and crest will overlap, trough and trough overlap, crest and crest overlap. You can draw and see that. Again, if there's a path difference, there could be some other point somewhere here, S2 to that point, S1 to that point, the path difference, that might be 2 lambda. Again, constructive superposition, crest and crest, trough and trough, crest and crest, trough and trough will overlap. There could be some other point further up, it will have a path difference 3 lambda. Again, there will be constructive superposition, crest and crest, trough and trough. Nicely you can draw and see if you want. If the path, that means if the difference between the distance traveled by the waves is integer multiple of lambda including 0, lambda, 2 lambda, 3 lambda, then at that point the waves will overlap in phase, that is crest and crest, trough and trough will overlap, and constructive superposition will occur. Again I am telling, if the difference between the distance traveled by the wave in space anywhere, if it is integer multiple of whole number multiple of lambda, at that point the two waves will overlap such that crest and crest overlap, trough and trough, crest and crest, trough and trough overlap, and so on. So there will be always constructive superposition will occur. Similarly, in space, any point, if the distance between the difference between the distance traveled by the wave, that is the path difference, is odd multiple of lambda by 2, then crest and trough will overlap, or trough and crest will overlap. At that point, destructive superposition will occur. So these distances are measurable quantity. You can measure by using meter rule. Practically, when you are doing it, you might have 2 loudspeakers. You can measure the distances. Practically, you can measure. Phase difference you can't measure. Remember that phase difference is not measurable quantity. Path difference is the measurable quantity. So very important, distinct factor that decides the type of superposition, and the measurable factor that decides the type of superposition is path difference, not the phase difference. But we have equation that relates path difference and phase difference mathematically, but the measurable quantity is path difference. So we must remember the required path differences in space to have constructive superposition, and the required path differences in space to have destructive superposition. You must remember that won't be given in the data sheet. You must remember. I'll write it on the board now. Okay, so to have constructive superposition, the required path difference should be 0, lambda, 2 lambda, 3 lambda, 4 lambda, and n lambda. That's n is an integer. So that's the difference between the distance traveled by the waves. When you measure by using meter rule, and if you know the wavelength, when you measure the distance from one particular wave source to the point P and the next wave source to the point P, and if you find the difference, if you get one of these values, if you know the wavelength, you are surely tell that that point you will have constructive superposition. Similarly, the required path difference to have destructive superposition is lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, or multiple of lambda by 2, remember them. But there's a mathematical relationship between path difference and phase difference that won't be given in the data sheet. Better remember that. That says the phase difference is equal to, phase difference we can denote by delta phi. Phase difference is equal to 2 pi over lambda times path difference. Phase difference equal 2 pi over lambda times path difference is the relationship between phase difference and path difference. So by substituting these values, you can find the required phase differences. Those are not measurable quantity, but anyway we can calculate it. The required phase difference to have constructive solution 0. When you substitute here, it will become 0. Phase difference 0. Lambda, if you substitute 2 pi, 2 lambda if you substitute, it's going to be 2 lambda if you use 4 pi, 6 pi, and so on. Here if you substitute lambda by 2, you will get pi, 3 pi, 5 pi. So already I told that when I started these lessons, these are the required phase differences and the relevant path differences. So you can put that, remember this equation, phase difference equal 2 pi over lambda times path difference. It's an empirical equation not given in the data sheet. So phase difference for constructive superposition, phase difference, we know that if the path difference 0, it's going to be 0. If it is lambda, then it's going to be 2 pi, 2 lambda 4 pi, 3 lambda 6 pi, 4 lambda 8 pi, n lambda we can say 2n pi. Same way it is phase difference for destructive superposition. If it is lambda by 2, it's pi, 3 pi, 5 pi, 7 pi, then it will be 2n plus 1 pi. This has a special name. This is path difference 0, means the waves have traveled same distance. So that is called central maximum, where the path difference becomes 0 and there will be constructive superposition, that is called central maximum. The questions in the past paper are very easy related to superposition. If there is a question related to calculation, it's simple. You need to find the path difference, but sometimes you might need to use geometry, something like Pythagoras theorem. I'll show those questions, I'll do those questions. Sometimes you might need to do Pythagoras theorem to find the distance. It's like a geometry, finding the difference distances from the source S1 to a particular point P, source S2 to the same point P. When you are finding the distance, you are using simple geometry or maybe trigonometry, whatever it is. Only thing you are finding the simple distances and find the difference between the distances and compare it with the wavelength. Then you can decide what type of superposition will occur at that point. Even the questions related to explanation in your past papers are related to path difference. The most of the questions, the similar answer comes. All the answers similar, actually the same way we explain, but different situations, different instances, but the explanation, the answers are the same based on path difference. So it's nothing hard. I'll discuss those few selected past paper questions now. Before that, I'll discuss one more factor, one more thing. Okay, so in this diagram I show S1, S2 are two wave sources, coherent wave sources. So they emit waves, so I'm going to explain in terms of wavefronts. Earlier I showed in terms of wave pattern, now this is about wavefront. So the two waves are overlapping. In my first lesson I explained about the wavefront. So the lines which I draw like a blue color are the wavefronts emitted by the source S1. The green color wavefronts are the waves emitted by the S2. So between two adjacent wavefronts, the wavefronts which is drawn indicates the crest. So between two crests there will be trough. And we know that crest and crest overlap constructive superposition, crest and trough will be destructive superposition. So we know at point X, two crests are overlapping. So at X there will be constructive superposition will occur. At X there will be constructive superposition. What could be the wavelength? What could be the path difference at X? So we'll see the path different for the blue color wave. This, if I say this is one, the distance between adjacent wavefronts is lambda. So if the wave has traveled a distance lambda from the wave source, so this is lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda. So the distance from S1 to X, S1x equal 5 lambda. S2x, so this is again for green color wavefronts. This is lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda. So that is S2x equal to 6 lambda. So when I consider the path difference by using these two distances, you will get 6 lambda minus 5 lambda, that is equal to lambda. So lambda means there will be constructive superposition. Already we learned that in my earlier. Right, so that is at X. When I consider at Y, what type of superposition will occur? At Y, you know that at Y, the green color line and the gap between the blue color lines. Green color line is a wavefront. So green color line is a wavefront means it's a crest between two blue color lines means trough. So the point Y is at a crest of the wave from S2 and a trough of the wave from S1. So there will be a destructive superposition because crest and trough are overlapping. So at Y there will be destructive superposition. So what could be the path difference? S1y, that will be lambda, 2 lambda, 3 lambda, 4 lambda, 4.5 lambda, 4.5 lambda. S2y, how much is it? Lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda. So the path difference that's going to be 5 lambda minus 4.5 lambda, that is lambda by 2. We know that if it is lambda by 2, there will be destructive superposition. Same way, we'll consider the point Z. The point Z, when I consider, at Z, what type of superposition occurring? It's constructive because Z is trough for the blue color wavefronts. Those are emitted from S1. It's between blue color lines, so it's a trough. Between green color lines, so it's a trough, and trough overlapping. So it's going to be constructive superposition. So we'll find the path difference. So S1Z, that is going to be how much? Lambda, 2 lambda, 3 lambda, 3.5 lambda. From S2Z, how much? Lambda, 2 lambda, 3 lambda, 3.2 lambda, 3.5 lambda. So if I consider path difference, that's going to be zero. So it's a central maximum. It's along the central line. So it's going to be central maximum, path difference 0. So constructive superposition. So you can see along this line, when I consider along this line, so where these points, we consider these points, crest and trough overlapping, crest and trough, crest and trough, crest. So along, this is crest and trough. So along this line, there will be constructive superposition will occur. Same way along this line, when you consider this, we'll consider this point like where we got destructive Y, this is this point, this point. So along this line, there will be destructive superposition. Along this line, there will be constructive superposition occurs. So here also the path difference between the two waves travel from S1 and S2 decides the type of superposition, and there will be constructive superposition along these points. You can see if it is a water wave, these wave fronts are created on surface of water by the ripple tank. You can see the superposition pattern at these positions. You can see the disturbance a lot. The water molecules are vibrating. But you can see at this position the water is calm, there is no vibration, you can see that. So there you can see there will be maximum vibration, then there will be a point like this one, you can draw and see like this is again destructive superposition between green and the line on blue, between green line on blue, between green line on blue. So along this one you will see a destructive superposition. Again, along this line, constructive superposition. Again, here destructive, you can see alternatively constructive, destructive are happening. So if you draw nicely by using proper way, you can see there will be alternatively constructive and destructive superposition occurs. And where if it is a water wave on ripple tank, where the constructive superposition occurs, there will be vibrations. You can see the disturbance like a ripples. You can see that where there is destructive superposition occurs along this line, you will see there is the water remains calm because destructive superposition. So here also the explanation all the same, nothing different, path difference decides the type of superposition. Okay, so next thing is about phase change during reflection. Anyway, a little bit better to know that if the reflection occurs from fixed end, later we'll use this when we discuss stationary wave. For example, when a string is attached to a fixed point on a wall or fixed point on a hook or whatever it is, there the reflection when it occurs, the phase change will be pi radians or 180 degree. What do you mean by that? That means if a crest approaches, when imagine you create a wavefront or pulse of wave, if a crest approaches the fixed point, then when it reflects back, it will become like a trough and reflects back. So the crest will become trough, a trough will become crest. That we say phase change is due to, phase change is equal to pi radians or 180 degree. This we call fixed end reflection. But if the reflection point is like something free end reflection, say for example, one type of rope is attached to another type of rope, maybe thing like this. A lighter rope is attached to, a heavier rope is attached to a lighter rope. Something like this. This is a heavier rope. At this point, it's attached to a lighter rope. So here when the reflection occurs, imagine you create a crest on it or pulse like this way. So when it reaches the boundary, because they are two different media, so whenever there is a different media, there should be partial reflection. When the wave pulse reaches the boundary of two different type of rope, there will be partial reflection and a partial transmission of wave to the second type of wave. So there what will happen, there will be reflection, I'll use the blacking for that. There will be partial reflection with small amplitude. Compared to that, this will be small amplitude. Partial reflection with zero phase difference. So then the wave will continue here also the same way. So there will be reflection with zero phase change. So there is no phase change in this situation whenever there is a free end reflection. But there are not much questions related to this type, but just I am telling it. And one more thing about reflection of light. When a light reflects, so for light, that also not much use in your past papers, but anyway, when light travels from higher refractive index medium to lower, we'll say like when a light moves from reflects from lower refractive index to higher refractive index. Say for example, when light reflects from air to glass, air-glass boundary. So this is the boundary. This is glass. This is glass. This is air. So if the light reflects from air-glass boundary, then there will be phase change of 180 degree or pi radians. There will be phase change 180 degree or pi radians. But if the light reflects from, this is about light, this is about light. If light reflects from the boundary where glass air, and if the light is moving from glass to air, this is glass, this is air. So if the light is moving from glass to air. In this situation, glass to air, there is no change in phase. So the change in phase will be 0. Phase change equal to 0. Here phase change will be pi radius. We don't use much this, but we better know that, because when we consider phase differences, we might know. Anyway, there are no such questions in the past paper, but better know that. Okay, so here the general way we explain the superposition pattern like that when we use two coherent wave sources. So S1, S2 are the two coherent wave sources. So along the center part of S1, S2, the path difference will be equal to 0. At that point, the path difference will be equal to 0. So if the path difference 0 means that is called central maximum. Then either side, we have D1, D1, mark D1, D1. So at this point, next one, next to the central maximum, when we have two sources, it could be two loudspeakers, or maybe double slit experiment, or maybe we might have identical dippers hitting water surface, whatever it is, same pattern of superposition happens. So along the center part of the two wave sources, the path difference equal to 0, which is marked O, central maximum, path difference 0. So this is first minimum. The next thing which happens is first minimum. There the path difference is equal to lambda by 2. Here also lambda by 2. Coherent wave sources S1, S2. Then the next thing is first maximum. There the path difference lambda. Here the path difference lambda. Remember the values in order. That happens in order. 0, lambda by 2, lambda, 0, lambda by 2, lambda. That's the way it happens in order. So next thing is second minimum. Second minimum means path difference 3 lambda by 2. This is 3 lambda by 2 here, second minimum. Then second maximum, path difference 2 lambda, path difference 2 lambda. So this is true. Next one is third minimum. Third minimum, it will be 5 lambda by 2. Here also third minimum 5 lambda by 2. Then after the third minimum, there will be third maximum, that will be 3 lambda, there will be 3 lambda, and so on. So remember the path difference and the relevant name for the superposition pattern. Central maximum, first maximum, second maximum, third minimum, third maximum, and so on. Same way, it's symmetrical about the central maximum on either side. Remember that. D stands for destructive, C stands for constructive, destructive, constructive. Okay, so now that's the end of theory related to superposition. Now we'll discuss few exam style questions. So this is an MCQ question. Two coherent sources emit waves of wavelength lambda in phase. So at the point where they are emitting, they are in phase among them. At a point where two waves meet, they have phase difference of pi by 2. Which of the following could be the path difference at this point? So, it's MCQ question. We know the equation that relates phase difference and path difference. So, we know phase difference delta phi is equal to 2 pi over lambda times path difference. I told that today, but they won't be given in the data sheet. Better remember that. So, phase difference pi by 2 equal to 2 pi over lambda times path difference. We'll put delta D, you can use here. So find the delta D, how much will it be? So that will be lambda by 4. Lambda by 4, correct answer D. Okay, so this is the second question. Diagram shows an experiment set up to demonstrate two source interference using microwave of wavelength lambda. So this is a microwave source, double slit they are using. So O is the central maximum. They are using a microwave detector So whenever it detects microwave high intensity, that is a constructive superposition, then the detector will show maximum reading. If it is a destructive superposition, it will be minimum or zero. Okay, they are moving the detector either up or down, but in this question they are moving from O upward direction. So O is the direction of upward arrow. The first position where the signal is a minimum. So first position, the word they are using, the first position where the signal is a minimum, so means first minima. So P is the first minima position. So equation that correctly gives. So first minima means, careful, from the central maximum first minima, the path difference should be lambda by 2. Path difference. When we give this question, most of the students they mark this one OP lambda by 2. No, that is wrong. Path difference, that is S1P minus S2P equal lambda by 2. Correct answer D. I gave just the path differences for first minima, first maxima, second minima, second maxima. You must remember. So according to that, first minima, that means lambda by 2. Okay, so this question read, these are two loudspeakers, L1, L2. They are connected to a signal generator. At 1 meter distance, there is a microphone. So laboratory microphone and the loudspeaker, they appear the same shape. So this is the microphone. It's connected to the CRO screen. So on the screen, you can see the wave pattern. If it receives a maximum, there will be a sine wave pattern on the screen. You will see a wave pattern on the screen like this. If there's no wave, so there will be nothing like this. The wave pattern won't be there. So frequency of the output of the signal generator is 1425 Hz. That means if the output AC signal, we know signal generator gives out AC signal. If the output is 1425 Hz, means the sound produced by L1 and L2 both will have the same frequency of 1425 Hz. They are generating coherent waves because both are connected to the same signal generator. So they are emitting coherent waves. Right, it's 1425 Hz when L1 and L2 are kept closer to each other. So when they are kept closer to each other, a clear wave pattern is observed on the CRO screen. So the microphone is kept along the mid portion of the loudspeakers L1 L2. So the path difference for the two waves from L1 and L2, the path difference, so L1 and L2, when you consider the path difference, that will be equal to 0 because both loudspeakers are L1 and L2 are kept closer, so they are at the same distance from the microphone, which is the receiver. So the path difference for the sound, which those are reaching the microphone, the position of the microphone, path difference will be equal to 0. Now what happens? So path difference 0 means it's constructive superposition, is it? So now so there's a clear wave pattern is observed on the CRO screen, something like this wave pattern. Okay, by keeping the L1 fixed, when L2 is moved towards microphone, so they are keeping L1 fixed, L2 is moving towards right, okay, through a distance of 12 centimeters. So now L2 has come to a position something like this. L2 would have come to a position something like this. This is L2. So this distance is 12 centimeter. This is 12 centimeter. So when it is moved to a distance 12 centimeter, the wave pattern on the CRO screen disappeared. That means there is no wave pattern. Now the wave pattern on the CRO screen, earlier it was like this. Earlier wave pattern was this, when the phase difference, when the path difference 0. Now when it is moved through 12 centimeter, when L2 is moved through 12 centimeter, there is no wave pattern, it's disappeared. Okay, so the wave pattern on the CRO screen disappeared first time. First time means earlier constructive superposition. The first time means first time there is destructive superposition. So you should know that phase difference equal to 2 pi over lambda path difference. So the smallest path difference that could give destructive superposition is lambda by 2. Smallest path difference that could give destructive superposition is lambda by 2, because first time the wave pattern disappeared means first time there is destructive superposition. So that means there is a path difference between the two waves from L1 and L2 to the microphone is lambda by 2. Okay, so first time. So lambda by 2, so the answer we can write this is the path difference, that is equal lambda by 2. So that is equal to 12 centimeter. So lambda equal 24 centimeter. So that is 0.24 meter. Now you know the speed of the, find the speed of the sound is the question. We know the frequency, which is 1425 Hertz. So use V equal F lambda for the sound wave. So frequency 1425, the wavelength 0.24, because it appeared first time means lambda by 2. If they say second time means 3 lambda by 2, 3 lambda by 2. Second time wave pattern disappeared means 3 lambda by 2, and so on. So you will solve this, you will get the answer, that will be 342 meter per second. Okay, so this question, fourth one, is an old past paper question. It's a January 2010 paper, January 2010, question number 18, this paper. January 2010, question number 18, old past paper, that is 6PH02. So the microwave source, it reflects from this point and reaches point S. Here another wave, microwave, reflects from here and reaches S. So actually practically there will be not only two waves reaching point S, there will be many other waves reaching, but in the syllabus we consider two source superposition. So that's the reason we consider only the two different microwave reaching point S. So the question, it says, assume no other microwave arrive at S. So that's given in the question. So they asked you wavelength of the microwave is 12. So explain why S is a cold spot. Means cold does not mean it's like a freezing. It means it's actually there is no heat produced. So explain means there's nothing to explain without any calculation. We have to do a calculation, so we'll do the calculation. We need to find the path difference. So all the calculations related to path difference I told, because path difference is the distinct factor that decides whether the superpositions will be constructive or destructive, and path difference is the measurable quantity. Okay, so the path difference means difference between the distance traveled by the waves. When I consider the first wave, it's traveling a distance 6 centimeter again. Sorry, this is 18 centimeter. That's a mistake in my question. This is 18 centimeter. I accidentally wrote something else. Okay, 18 centimeter. So this wave is traveling 18 centimeter, then 6 centimeter. So the total length traveled by this wave is 18 plus 6. This is traveling a distance of 30 centimeter, then 12 centimeter. So we can find the path difference at S. So the wave is reaching the point S. So path difference at S equal, so this length 30 plus 12 is longest, 30 plus 12, that is the distance traveled by one wave. The second wave 18 plus 6. So this will be 42 minus 24, that will be 18 centimeters. So that's a path difference. Okay, we know path difference, if it wants to be constructive superposition, it should be integer multiple of lambda. If it wants to be destructive superposition, odd multiple of lambda by 2. Okay, so we'll see, this is 18 centimeter. In terms of wavelength, how much is it? We know the wavelength, that is 12 centimeter. So path difference, if we want to give it in terms of lambda, we'll divide by 12 multiply by 12, that is lambda. This 12 lambda I'm going to replace later. So divide by 12 and multiply by 12, because 12 and 12 get cancelled, I'll get 18. So this is actually, I'm going to put it as lambda next step. So 18 divided by 12 is going to be 3 by 2. you can divide by 6362. So 3 by 2 is 20 lambda, 12 is lambda. So it's going to be 3 lambda by 2. So that is 3 lambda by 2 means odd multiple of lambda by 2. So there will be destructive superposition at S since the waves overlap antiphase. So if it is this way, destructive superposition, why the waves will overlap antiphase. So cold spot, therefore S is a cold spot since they cancel each other. Amplitude equals 0. If you want, you can say amplitude 0. Okay, L1 and L2 are two loudspeakers at a distance of 20 centimeter apart. Both are connected to the same signal generator, so they are emitting coherent sound waves. The frequency of the signal generator output is 3385 Hz. O is the central maximum. The distance between the two loudspeakers is 20 centimeter given. So the microphone is kept here and it can move along this line. The line of movement of the microphone from the line of connection of two loudspeakers is 50 centimeter. This length is 50 centimeter. That also given in the question. So when the microphone is at the central O, there is a wave pattern on the CRO screen. But when the microphone is moved towards point B and when it reaches the point B, which is 30 centimeter from O, first time it detects a minimum. So first time it detects a minimum means it's lambda by 2. That's the first minima. Find the speed of sound in air. So they are nothing again. So we need to find the path difference. So path difference we want to find. We need to find this distance L1P. We need to find this distance L1P. We need to find this distance. We need to find. Also we need to find L2P also. L2P also we need to find it. So these are the two things we need to find in order to find the path. L1P and L2P we need to find. Okay, so here nothing, only thing in terms of waves we need to find the path difference, but here little bit of difficulty there in finding path difference because little bit of geometry we need to do, we need to use. O is along the center of L1, L2. We need to take that. O is the central maximum. So microphone detected maximum means O is the central maximum. That is path difference 0. So it should be at the center part. Okay, so we need to find this distance. We know 30 centimeter from this to this point is 30 centimeter. I need to find this L1P means we'll make an adjustment like this. I need to find this distance. So this is 30 centimeter. From here to here 20. From here to here 20 means from the center, from here to here, this is 10 centimeter. So from here to here 30 centimeter. From here to here 30 minus 10, 20 centimeters. So this height, so if I make this point as this is already L1, L2P. If I name this point as Q, QP, QP1 is equal to 20 centimeter. I need to find this distance L1P. So I can say L1P squared is equal to L1Q squared plus QP1 squared. So L1Q squared, this length is 50 centimeter, 50 squared. Q1, P1. So from here to here that is 30, from here to here 10 because half of 20, this from between the two loudspeakers, the distance is 20 centimeter. This is 10 centimeter. So QP1, QP1, sorry, not QP1, QP is equal to 30 minus 10, 20 centimeter. So 30 minus 10, that is 20 centimeter. So it's a Pythagoras theorem I'm using. So I need to find the L1P, that is equal to L1P, take square root, you will get 44.7 centimeter. Sorry, that is 53.9 centimeter. L1P is 53.9 centimeter. Same, I need to find L2P, this length. So from here to here 30, this is 20 means this length. So here this is 50. So this length how much? From center to this line, this is how much? Half of 20, that is 10 centimeter. So in this right angle triangle, I can use the Pythagoras theorem for this right angle triangle. This is 50 centimeter. This is 30 plus 10, 40 centimeter. So L2P squared equal 50 squared. Or I can say that one L2, this is P, this is Q, this is R, name this R. So L2R squared plus RP squared. L2R, that is 50 centimeter, 50 squared. RP, that is, this is 30, this is 10. So 30 plus 10 all things squared, that is 40 squared. So from this L2P, you will get 64 centimeter. 64.04 or something, 64 centimeter. Okay, so the path difference for the wave at P, path difference equal L2P minus L1P, that is 64 centimeter minus 53.9 centimeter is going to be 10.1 centimeter. 10.1 centimeter. That is equal to path difference. So we are getting first time. First time there is minimum. First time, the word first time is used. So first time means it's lambda by 2. First time they are saying, that means the path difference is lambda by 2. So lambda by 2 is equal to first minima. So path difference lambda by 2 is equal to 10.1 centimeter or 0.101 meter. So from this find the lambda, that is 0.202 meter. Use E equal F lambda. The frequency is 1693 Hertz. 1693 Hertz, not the earlier one. So V equal F lambda will use V equal F lambda. So F is 1693 into 0.202, you will get the speed, that will be 341 meter per second. So almost 342 meter per second. So frequency 1693 Hertz. So only thing here, the geometry comes finding the path difference. We are using Pythagoras theorem, that's all. That's the difficult part here. Otherwise, in terms of waves, there's nothing new. Okay, so this is from Edexcel past paper, that is June 2015, question 6 in WPH 0201. So this diagram is given. A teacher demonstrating superposition set up two speakers in a laboratory. The students stood in different positions throughout the laboratory. The teacher played a single note through one of the speakers. The teacher then played the note through both speakers and asked the students to describe their observations. Students in some positions said that the sound got louder and students in other positions said the sound got quieter. The students noted positions of louder sound capital L and quieter sound capital Q. Their results are shown in the diagram. So this diagram is given. The wavelength of the note is 0.8 meter. The following distance were measured: x1 to L1. x1 via two loudspeakers, x to L1 1.6, y to L1 2.4, x to q1, that's a quiet position, is 1.7, y to q1 is 2.1 centimeter. Using the distances given, explain why L1 is louder and q1 is quieter. Okay, so here again we need to find the path difference. A 4-mark question, nothing. We need to find the path difference for both L1 and L2. Separately find it from x and y. Say for example, I need to find the path difference of x L1, y L1. Find the path difference and compare it with the wavelength, which is 0.8. Same way x q1, y q1. Find the path difference and compare it with the wavelength 0.8. So when I compare it, I should get, for L1 is a louder, I should get integer multiple of lambda, that is integer multiple of 0.8. For this one I should get, for Q1 I should get odd multiple of lambda by 2. That's all. Okay, so we'll answer this question. So path difference at L1. So path difference at L1, that will be YL1, because that is longer distance, minus XL1. YL1 is given as 2.4 minus 2.4 meter, is meter not centimeter. So all are meters, I wrote in the wrong way. Those are meters, 2.4 meters, all in meters. So 2.4 meter minus 1.6 meter. So 2.4 meter, YL1, XL1, 1.6. That's going to be 0.8 meter, that is lambda. So at Q1, but at L1, constructive superposition will occur, because it's path, since the path difference equal to integer multiple of 1 times multiple of lambda, means the waves will overlap in phase. So at L1, waves will overlap in phase, and constructive superposition will occur. So there will be a louder sound. So there will be louder sound. Okay. Same way, path difference for Q1, find it. So I'll raise this. So this is the answer you need to write for L1. So same way you need to write for L2. I'll raise this and write it here. Okay, so about, I'll continue the answer. So then add a path difference at Q1. So at Q1, that's a quiet region, YQ1, YQ1. So I raised it from the loudspeaker, YQ1 minus XQ1. So YQ1 is given 2.1 meters minus 1.7 meters. So it's going to 0.4 meter. The wavelength is 0.8. So it's a half the wavelength, lambda by 2. So you should then say at Q1, waves will overlap antiphase. Destructive superposition will occur. Therefore, quiet region. Okay, so these are the questions related to calculation, but whenever there is a question related to explanation, say for example, I am not discussing all these questions. There's a question made 2012, question 16, that is about water waves are overlapping, passing through gaps, and the photograph shows there's a beach given a photograph. Waves can be seen passing rocks on their way to the bench. The uneven surface of the sand has formed as a result of diffraction and superposition of waves. So actually after passing through the gaps, the waves are overlapping. The soil is disturbed like a bump, alternative bump. So the question is explain the shape of, use ideas of diffraction and superposition to explain why the sand surface becomes uneven. This is May 2012, question number 16, 6PH02. Anyway, whenever there is a question related to superposition, explanation type questions, the only thing you need to talk about path difference. So you should say the waves are diffracted through the gaps between the rocks and they overlap at a point. The distance of the point from the two gaps of the between the rocks, if the path difference is equal to integer multiple of lambda at that point, the waves will overlap in phase, constructive superposition will occur, the water particles will overlap with large amplitude and they push the soil away from each other. Then if the point at which the path difference of the point from the two gaps between the rocks, if it is odd multiple of lambda by 2, the waves will overlap antiphase, destructive superposition will occur. So the amplitude will become almost equal to 0. That region is calm, so the soil will not be disturbed. So like that, whenever there's a question related to explanation questions related to superposition, the answers are almost the same. You need to talk about path difference, then compare the path difference either with odd multiple of lambda by 2, integer or integer multiple of lambda. If it is odd multiple of lambda by 2, at those points destructive superposition will occur, so the amplitude will be almost equal to 0. If the path difference is integer multiple of lambda, at those points constructive superposition will occur, waves will overlap in phase, so amplitude will be larger. So same answer, the same type of answers you can see in all questions related to explanation type of questions in superposition. So I hope this is enough for superposition. So I'll continue the next lesson. You can navigate to any of my lessons by using the playlist of the channel, and you can write any comments related to this, whether you understood or not. You can write the comments. Okay, if you subscribe my video channel, you will get notification when I upload new videos. Bye.